I'm going to be talking about a repressible operon. An example of this is how E. coli uses tryptophan as nutrients. And tryptophan is an amino acid that is created in an anabolic pathway. And this repressible operon creates tryptophan using negative feedback inhibition. So what happens first is that the regulatory gene is transcribed into mRNA, and this mRNA can then be translated into a repressor protein and an active repressor protein. So this means that this repressor protein cannot bind to the operator. It can only bind if tryptophan is present in the cell. So if tryptophan is present in the cell, a precursor tells the E. coli that whether tryptophan is present or not. So if it is present, it binds to the repressor protein as a co-repressor, giving the repressor protein an allosteric change and activates the repressor protein. So this means that the repressor protein cannot bind to the operator, turning the operon off because the RNA polymerase cannot bind to the promoter. And this prevents transcription and further on translation from occurring to make more tryptophan. But if tryptophan is not present in the cell, the repressor protein is inactive. So that means it cannot bind to the operator. So this means that the RNA polymerase can now bind to the promoter, and it can transcribe these genes into mRNA, and this mRNA can then be translated into enzymes needed to make tryptophan for the E. coli. Okay. Another type of operon is called the inducible operon. An example of this is when humans consume lactose and E. coli wants to catabolize or break down the lactose, and obviously it uses a catabolic pathway. So what happens first is that the regulatory gene is transcribed into mRNA, and this mRNA is then translated into a repressor protein. But unlike the repressible operon, this repressor protein is always activated when lactose is not present in the cell, and this prevents transcription and furthermore translation from occurring because the RNA polymerase cannot bind to the promoter. So this is what happens when lactose is not present in the cell. But when lactose is present in the cell, an isomer of lactose called allolactose acts as an inducer and binds to the repressor protein, giving it an allosteric change, and this means that the repressor protein can get off the operon because it doesn't have the shape for it. So when the repressor protein is off the operon, this means that the RNA polymerase can now bind to the promoter, and transcription of the genes can occur. And this mRNA is then translated into 3 enzymes needed to break down lactose. Now, the inducible operon and the repressible operon both use negative feedback inhibition because the regulatory gene when the regulatory gene is active, it turns the operon off, and it will only be positive if the regulatory gene was on and the operon was on in order for the transcription of the genes to occur. But since the repressor protein is always off when the operon is on, that means this is negative feedback inhibition. So lactose is also involved in a different type of gene regulation that is positive. So in the E. coli cell, E. coli would preferably like to use glucose as a source of energy, and it breaks it down in a catabolic pathway. But if glucose is scarce in the cell and lactose is more present, then the concentration of this molecule called cyclic AMP will increase. So there is a regulatory protein called the CAP, and it is inactive. So it will only be active if cyclic AMP, also known as CAMP, is present in the cell. So if cyclic AMP is present in the cell, meaning that the concentration of lactose increases, then it will bind to the CAP protein, and it will give it an allosteric change, and this active protein can now bind to the promoter. And now this binding of the active cap protein to the promoter allows RNA polymerase to have a higher affinity to binding of the promoter, and it then can transcribe and translate the genes into mRNA, and thus the mRNA can be translated into enzymes that can break down the lactose for energy. But if the concentration of glucose is increased and lactose is also present in the cell, the concentration of the cyclic AMP or the CAMP will decrease, and it will come off of the cap protein, and it will inactivate it. It will give an allosteric change and it will activate the cap protein. So this cap protein can no longer bind to the promoter because it's not activated. So the RNA polymerase has a lower affinity to the binding of the promoter, so the binding will have a lower rate. So this means that this E. coli will use glucose instead of the lactose, and it will have little to do with the lactose enzymes. So this is an example of positive gene regulation because this activated regulatory gene, when it is activated, it binds to a promoter and it turns the operon on. Unlike the other operons, unlike the other negative gene regulations, when the repressor protein was active, then it turned the operon off. But because when this is activated, it turns the operon on, it makes it an example of positive gene regulation.